In this video, we're going to discuss how hypotheses involving intercept and slope parameters can be tested using a t-test. We'll be discussing both one-tailed and two-tailed tests, but we'll start with a two-tailed test. Let's talk about how a two-tailed test is conducted. The general form, as we noted before, is we're testing whether beta j equals c or is not equal to c. So we form the t-statistic, but we do that under the assumption that the null hypothesis is correct. So what we do here is we replace the beta j on the right-hand side at the top of the t-statistic with the value c. So you construct the t-ratio, which is equal to the estimated parameter received from your regression model minus the hypothesized value, and we divide that by the standard error of that particular parameter. So that would be the t-statistic. And then we compare that to the critical values. And the critical values are ones where if we're using a significance level of alpha and it's a two-tailed test, we find the values of t alpha over 2 and negative t alpha over 2, where half of the area is above the critical value and half of it is below the negative of that critical value. So for example, if the critical value is 2.03, then you would reject the null hypothesis if you get a t-ratio that's more than 2.03 or less than a negative 2.03. In other words, if the absolute value of your t-statistic exceeds 2.03, you reject the null hypothesis, and under the null hypothesis, this type of error would occur alpha % of the time. So you only reject the null hypothesis if it falls into one of the rejection regions in either of the two tails. And notice, by the way, it says you do not reject the null hypothesis, or you reject it, you never accept the null hypothesis. Keep that in mind. We want to be precise in this definition. So here, if we take degrees of freedom of 30, just as an example, these are the critical values at different thresholds. So if you use a 10% significance level, the critical value of the t-distribution is 1.697. So you reject the null hypothesis if it's above 1.697 or below a negative 1.697. And a type 1 error would occur 10% of the time because there's 5% above and 5% below those two values. If you're using a 5% significant level, the critical value changes to 2.042, and 2.5% of the area falls in either tail for a total of 5%. If you're using a 1% significance level, you find the value where a 0.5% falls in either tail, and the critical values, again, for 30 degrees of freedom would be 2.750. If beta j equals 0, we get exactly the same type of thing, except we replace the value of beta j in the t-statistic with 0, because that's what's hypothesized under the null hypothesis. So we write the t-statistic as beta hat j over sigma hat sub beta hat j. And this is what we normally refer to as the t-ratio. Every regression package out there computes the t-ratios for your intercept and slope parameters, and they're reported in your regression output. If we're dealing with a one-tail test, it's very similar. We could test for whether something is significantly above c or below c. And what happens now is if we're dealing with a test where the null hypothesis is greater than or equal to some value, then you find the t-statistic where all of the area lies below that value. Notice you end up with all of the area just on one side of the distribution. In this case, you'd find the value where alpha % of the area lies below your critical value, and we don't have to worry about the other side, because if you're testing whether something is greater than some critical value, if it's dramatically greater than that, that would not cause you to reject the null hypothesis. So all of the rejection area is on one side of the distribution. The larger area on the one side and no area on the other side is used to reject the null hypothesis. If you're testing versus 0 again, you still use the t-ratio, and the rejection region is only on one side of the distribution. And this is just the opposite case when you're testing whether something is below some threshold value. Here, the whole rejection region lies on the right tail of the distribution. So you form the t-ratio, either where beta j minus c over the standard error of beta j, or simply beta j over sigma hat sub beta j, or the standard error of beta j, if you're comparing it to 0. to see whether something is significantly positive or not. Whether you use a one-tailed or two-tailed test ultimately comes down to a question of whether the underlying model that you're using predicts that there's a significantly positive or significantly negative effect, or if your model predicts that there's some upper or lower bound to the value that a parameter could take. In those cases, you'd only reject the null hypothesis if the evidence you find is the opposite of what the null hypothesis specifies. So it's always going to be just on that one side of the distribution.